Hello students, today we are going to study about the linear independence and the linear dependence. Alright, so suppose you have a collection of vectors and vectors can be, this collection can be either linearly independent or linearly dependent. So first condition we will see for linearly independent. Alright, so suppose say you have a vector and the set of vectors are like v1, v2, vn, so on up to vn, and they are linearly independent. So they are, if the equation involving the linear combination say a1 v1 plus a2 v2 so on up to an vn. So whenever you perform this operation of the linear combination, the answer if it is equal to 0, then I can say that it is linearly independent. All right, if it is linearly independent. Now we'll check for linear dependent. So if the vectors are linear dependent, the equation has a solution when at least one of the scalars are not equal to 0. That means in the place of 0, if I have some value k, then I can say that the equation is linearly dependent. All right, so this is about linear independent and dependent. Now let us take the first example, that is we have to check whether the vectors are linearly dependent or independent. So the solution will write in the first, we will write the general form, that is a1 v1 plus a2 v2 so on up to an vn is equal to 0. That is for linearly independent solution. So what is a1? A1 into v1 is first vector, a2 plus 408, that is second vector, plus a3 3 1 minus 1 5, that is a third vector, is equal to 0. All right, now we will write these vectors in the matrix form. So what is the matrix form? 1 minus 2 0, which is nothing but our ax, that is our augmented matrix form, right? So first we will write the, so that is 408 3, sorry, it should be 3 minus 1 5, and it should be augmented matrix means we have to write it here 0. All right, okay, now what we have to do is we have to apply the reduced row echelon form, which is like every matrix ka, this is the first step that you have to apply, okay, if it is not in the reduced row. Now apply that. So row 2 changes to 2 times row 1 plus r2. So what, so row 2 will change now. So the first row will remains the same, 0. Now the second row will become 0 8 and 5 0, right? Yes, 0, it is 0 8 5 and 0. All right, yes, now I will try to change the third row, that is row 3. So row 3 changes to row 3 minus r2 or minus r2 plus row 3, anyhow. So 1 4 3 0 0 8 5 0 0 0 0 0. Okay, now I want to change this 8 to 1. So what I will do is r2 changes to it is 1 by times r2. So 1 4 3 0 0 1, it is 5 by 8 0 0 0 0 0. Now I want to change this 4 to 0. Can I do that? Yes, I can do that. So r1 changes to r1 minus 4 times r2. So what I will get, it is 1 4 3 sorry, here it is 1 0, and if I apply the the row form, it will be, okay, the answer should be half 0. All right, so 0 1 5 by 8 0 0 0 0 0. Okay, so I hope this is already in the reduced form. I need not further reduce it, and now I will write the equation. So 1a1 plus half of a3 is equal to 0, and 1a2 plus half 5 by 8 of a3 is equal to 0, and a3, let me consider some constant k. All right, k can be any value. So let me rewrite a1 is equal to minus half of a3, where a3 is nothing but half of k, and let me write for a2 as well, it is minus 5 by 8 times k. and A3 is K also, as usual. So let me write the matrix. So half minus half K, 5 by minus 5 by 8 K and K. So K can be any value. K can be from 1 to n, and it is very clear that if it is 1 to n, you are not getting any value that is equal to 0. Therefore, it is non-trivial solution, and it is linearly dependent. All right, we'll move on to the second example. So second one is a similar one, and we have to check whether these vectors are linearly dependent or independent. So the solution as usual starts with, you have to write it in the a1 b1 form. So a1 and the matrix directly I will write, plus a2 the second vector 0 1 1 1, and a3 the third vector, that is 0 2 0 1 7, is equal to 0. That is in the linear combination formula. Now we will write the equation or the vectors in the matrix form. So 1 2 1 4, 0 1 1 1, 2 0 1 7, given 0 0 0 0. Now what we have to do is we have to apply the row operation. So the row 2 changes to r2 minus 2 times r1. Then row 3 changes to row 3 minus r1. Row 4 changes to r4 minus 4 times r1. So we will apply, the first row remains the same, so 1 0 2 0, and the second row changes to 0 1 minus 4 0, third row 0 1 minus 1 0 0 1 minus 1 0. All right, now what we have to do is we have to apply for the row 4, that is row 4 changes to row 4 minus row 3. So what you will get, the answer will be, first row remains the same, so we'll write it down, 1 minus 4 0 0 1 minus 1 0. The last row becomes 0 0 0. All right, now what we have to do is I have to apply the row operation for the third row, that is row 3 changes to row 3 minus row 2. Okay, so what I will get, so 1 0 2 0 0 1 minus 4 0 0 0 3. Okay, it is 3 0 and 0 0 0 0. All right, now I want to change this 3 so to 1. So let me change it as r3 changes to 1 by 3 times r3. So first row 1 0 2 0 0 1 minus 4 0 0 0, it is 1 0 and 0 0 0. Now I want to apply the row operation for the row 1 and row 2. I'll try to make them as 0. So r1 changes to r1 minus 2 times r3, and r2 changes to r2 plus 4 times r3. Oops, 4 times r3 plus. All right, now the matrix will change as to, okay, it is 1 0, okay, it is 0 0. Second row will be 0 1 0 0 0 0 1 0 0 0 0. All right, now it is already in reduced form, therefore a1 is equal to 0, a2 is equal to 0, a3 is equal to 0. Therefore it is a trivial solution, and that and I can say that hence linearly independent. So that is all, students. I hope you like the video. Stay tuned for the more videos. Thank you so much.